Hi. Yes, I'm Chris. I work for OVO Energy in London. We're an energy supplier with a focus on renewable energy. And I'm going to talk about bring your own effect. But before that, I just want to very quickly spam you about a conference that I'm organizing. It's in London on the 1st of September. It's called Lambdale. So if you like functions and beer, then please come. And the CFP is open. We're looking for speakers, so please come and talk. So I'm going to talk about this technique called bring your own effect, which is becoming increasingly popular with functional libraries in Scala recently. Libraries like FS2 and HTTP for S are using this technique to allow the user of the library more flexibility in choosing the effect, or the monad, essentially, that they want to use when they're using the library. I've also introduced this in a library that I maintain called ScalaCache, so I'm going to talk a little bit about how it works and how I did it. I'd like to start by reminiscing about the good old days before I even found Scala. I was writing Java for a long time, and in those days, futures did exist, but they were pretty terrible. All you could do is call get and just block until it completed, so they were basically pointless. So if I was to design a caching API in Java back in the day, it would probably look like this. No futures anywhere, nice and simple. Call get, give it a key. It will block if it's doing like a network request to talk to Redis or Memcache or whatever. It might block forever if the network is down. It might throw an exception, who cares? But at least it's simple. But then I found Scala, and around that time, the Reactive Manifesto came out. Does anyone remember the Reactive Manifesto? Did anybody sign the Reactive Manifesto? I did. So as soon as that came out, suddenly everything has to be a future, because if it's not a future, you're not reactive. So an equivalent API in Scala would probably look more like this. You're signaling that this thing is happening asynchronously because you might be doing some I/O to interact with your cache. You might be doing a network call or something blocking. So you'd return futures. But then sometimes you know that you're not actually doing any network I/O. You're just talking to, say, Caffeine, which is an in-memory Java cache library. So you know that it's not going to throw any exceptions, it's not going to take seconds, it's going to return in nanoseconds and just give you your answer. So wrapping it in a future is just a bit pointless. It's annoying to work with. So maybe a more useful API would look like this, where you had like an async version of your API and a synchronous one, and depending on your cache implementation, you would implement the appropriate one. So that's one option for dealing with this kind of duality of synchronous and asynchronous. But then another way of looking at it is, let's look at it from the user's point of view. The user of the library doesn't necessarily care whether they're talking to Redis or Caffeine or whatever. They care about, like, in this situation, in my particular use case, I want a future or I don't want a future. So if they are already doing asynchronous stuff, like they're working in Play framework or whatever, maybe a future makes more sense to them. So they would use the top API there, the cache trait, which returns futures. But then maybe they are dealing with synchronous stuff and they don't want to bother with futures. So they would just use these synchronous wrappers down at the bottom, these helper methods that just wrap the API and make it synchronous, so it's more convenient to work with. So this is actually what I did originally in ScalaCache, and it's not very elegant having two copies of your API. Basically, you have like your main API and then this whole big copy of it, which is just wrapper methods around the main API. I didn't really like it, but I did it anyway. I thought, well, at least there's only two copies. There's the synchronous one and the non-synchronous one. How bad could it be? But then along comes a Scala Z user. This guy, he wants to use Scala Z task. He's not happy with the Scala built-in future for various reasons. So he wants to use task. But then this guy comes along, he's a cats user, and he wants to use the cats effect IO, or maybe he wants to use eval, or who knows. Or maybe he's a Monix user, he wants to use a Monix task. So over the last few years, there have been more and more of these different effect monads or effect containers popping up, and I couldn't possibly cater for all of them, just make dozens of copies of my API, wrapping different things in different things. That's silly. So really what I want to do is something more like this. I want to abstract over this effect container, just call it F. This F with an underscore in square brackets, that's a higher kinded type, so that's like an F of something, like a future of integer or whatever. So I just want to say, for some effect type F, my get method is going to return an F of an option of the value, and similarly for put. And then, as a user of the library, you could say, I have a cache of string keys and integer values. I want to do a get, and I want it to return me a future. Or I want it to return me a Monix task, or whatever. So it gives your users a lot more flexibility. They can choose what effect is most appropriate for their program. One question remains here. What do you do when you just want a plain old value? You don't want it to be wrapped in a future or a task or anything. You just want like the good old-fashioned synchronous API. It's not really clear what you should put in the box with the question marks. But in this case, there's a handy thing called the identity functor, or identity monad, this thing called id, which is just defined as type id of A equals A itself. And it's kind of a stroke of luck that the compiler actually lets you do this. So then you would just say get with type id, and it would give you back the value itself, not wrapped up in anything. So let's try actually implementing one of our cache backends in ScalaCache using this new technique. So we have some memcached client that we've set up. We're connected to memcached. We need to implement get. We're given this f type, and we need to return an f of option of v. So how on earth do we do that? Because we don't even know what f is. Are we returning a future or a plain old value or a task? Who knows? So we need a bit more information. This is just a bit too minimal. We can't work with this. So what we need is a type class of f, which gives us some ways we can work with f. So I don't know what f is, but I know that I can do certain things on it. I can call methods on this type class, which will kind of do things like create a new instance of f, given a value, or map an f, or flat map an f, or whatever. So here I'm assuming this type class has a function called pure, which will take a pure value and turn it, like wrap it up in an f. So the next question is, what type class do I actually need? There's an awful lot of them out there. And the answer is it depends. It depends on what your code actually needs to do. And in general, the good rule of thumb is to use the least powerful tool for the job. So don't just instantly reach for monad if monad is not actually what you need. Maybe you only need an applicative functor, or maybe you need a monoid. Who knows? It depends on your situation. So these ones I've listed here, these are listed in increasing power from top to bottom. So we start with functor. All you can do over that is map over that. So it has a map function. Then you have an applicative functor, which builds on top of functor. So it has a map, but it also has this pure method, which means you can now construct instances of f. You can take a value and you can wrap it up in an f. The next step is good old monad, the M word. This adds a flat map method, also called bind. So now you can flat map over things. The next one down is monad error. So this takes monad and it adds the power to raise errors and handle errors. So it's adding error handling. And then the bottom two are probably less well known, sync and async. These are, I based them on type classes that are in the cat's effect library. So sync, this means do some synchronous I/O, but delay that until you actually, defer the effect until you actually want to execute it. So it's got this delay method, which takes in a thunk, or like a zero argument function, saying, I want to do this bit of I/O. And at that point, when you call the delay function, it doesn't actually do the I/O, it just builds up a description of the I/O that you want to do later, at the end of the world, when you actually run execute your program. And then the final one, async, has this really weird looking signature, which I will explain in a second. So a quick aside about what this async thing is all about. So there's a few different ways that you can do blocking or long-running operations like I/O. The simplest one is just like good old Java. You can just block the current thread. Just call the function and wait till it returns, and you've blocked your current thread. You can't do anything until the function returns. And then another way that you can do it is to wrap it in a future, which still blocks a thread, but it doesn't block the thread you're on right now. So it'll go away and run on a thread in a thread pool somewhere, and eventually it will complete or fail. While it's doing that, you can carry on doing stuff on the current thread. But then the third, the most powerful way that you can do this kind of I/O or long-running operation is by using callbacks. So this should be familiar to you if you've done any kind of Node.js or that kind of stuff. So you say, start this remote API call, but I'm going to give you a callback to notify me when you've finished. And this can happen without, depending on the implementation, this can happen without blocking any threads at all. It can just, it'll all be done using low-level network interrupts and so on. So when the response comes back from the server or whatever, the callback can be called, and no threads were used in the process. So this is a way to be more scalable. You can have a lot more concurrent operations in process at the same time, not worry about running out of threads. And it's worth pointing out that the two top ones, blocking the current thread and running in a future, they are kind of isomorphic to each other. You can switch between them. If you have some code that blocks the current thread, you can just wrap it in future, and that turns it into a future, or going the other way, you can call await on it, and that takes it back up to blocking the current thread. But the callback-based async I/O is not like that. That's strictly more powerful. Because you can go from callbacks to a future using promises, but you can't go the other way. You can't take code that blocks a thread and just magically turn it into code that doesn't block a thread. So this callback-based version of doing I/O is the most powerful tool that we have. And that's why we end up with this weird signature down here, this register thing. So this is registering a function that, given a callback, will do some I/O. So this is a way of an API to let your users do this callback-based I/O if they want to. Okay, so for ScalaCache, I ended up using this async type class here. It's very similar to the one that's in cat's effect with some minor technical differences. And then I just implemented instances of this type class for a few different commonly used effect types. So here's one for the standard Scala future. So we've got pure, map, and so on. And then the async one is doing this callback stuff that I talked about just now. There's also a synchronous example. So this is for caffeine, which is an in-memory cache, so it's very quick and doesn't throw exceptions. So it's safer and more performant to do this in a synchronous way. So I'm calling this delay function, and then inside the delay block, I'm just doing like very standard code to like look up in the cache using the key and deserialize the responses, the value, and so on. So that's the kind of two different styles of caching that ScalaCache supports. There's the synchronous one here and the asynchronous one based on callbacks. But from the user's point of view, it doesn't really matter which one of these you're doing in the implementation. Oh, sorry, that didn't make any sense. Sorry, there's the caffeine one, that's the synchronous one. There's the asynchronous one. So this is the memcached implementation. This is using a library called spy memcached internally. So it's using this async block, and then given a callback here, CB, it does an async get using the underlying client, and that returns a future which you can attach a listener to. So you add a listener into the future, and when it completes, either successfully or otherwise, you call the callback that you were given, and you give it either the result or the error. Okay, so that's all I'm going to say about ScalaCache, but that's how I did this, but I guess you need a bit more kind of persuasion about why you would want to do this kind of thing yourself. So I think there's a few different use cases for this kind of abstracting over the effect that I've been talking about. So in a library like ScalaCache, the main benefit is that you get more flexibility for your users. They can choose whether they want to use like a synchronous mode or Scala futures, task, I/O, whatever they want to use. So it kind of fits into what is most appropriate for them. But then I think this kind of technique of abstracting over your F is also useful when you are writing applications for yourself, when you are the user of this code. And that's because it gives an extra dimension of abstraction, which I'll try to explain in a second. It can also help to make your code more testable, but I don't really have enough time to talk about that today. That's probably a separate talk in itself, so I won't talk about testing. So what do I mean by an extra dimension of abstraction? What I mean is that it decouples three things from each other. So you've got, the most important thing is your business logic. This is what's actually providing value to your users. And generally what business logic comes down to is composition of operations. I want to do this thing, and then do this thing, and then if that succeeds, I want to do this thing, and so on. That kind of sequential composition and occasionally branching, maybe doing things in parallel, that sort of stuff. So that's the most important part of our program, and we want to keep that as clean and as simple and abstract and pure as we can do. So this technique can help to do that. Then another kind of aspect of your program is often the choice of effects that you need to provide. So, for example, you might need to do some error handling, and you might need to pass some context around within your program, like configuration or whatever. It kind of depends on your program. And then there's concrete implementation details like low-level HTTP clients and databases and that kind of stuff. So I'm just going to go through a kind of simplified worked example. We've got some kind of user service that can create and manage users of your application or your company, whatever. So when we create a user, we want to save it to persistence, the database or whatever, and we also need to send an event on a message queue, broadcast an event saying this user was created. So we're going to model that using this like abstracting over F technique. So we've got different traits for different like parts of our domain. So we've got one for persistence, which can do things like saving users and finding users by ID. And this is abstract in F. So all of the the result types on the API they're all F of something. And then we have a similar one for sending events. So send created user event returns an F of unit. It's unit because sending event is a side effect. There's not really anything you can return from that. And then we can construct our program. I call it user ops. Sometimes it's called an algebra. The naming is a bit fluid. I don't think there's really much convention around this at the moment, but I think that will evolve. So it's abstract in F. It takes in the things that it needs, the lower level kind of primitive operations that it needs to use, like persistence and events, and then it composes them sequentially. So it's to create a user, given some details about that user, it needs to save the user to the database, look the user up again because it's not a very good database, so we have to save it and then look it up again, and then send an event about that user. And because we want to do this sequential composition, we are using a monad here. So we have this, this context bound here, this type class restriction saying, I don't care what F is as long as it's a monad. So that is our business logic right there, and it's quite clean because we're not too worried about what F might be. It might be a really complicated monad transformer stack, but we don't care, as long as we can compose the things sequentially. Then the next step, I guess, is choosing what effects your program needs. So for example, you might need some error handling. So you might have user service failure type, where you can fail in a few different ways, like the user doesn't exist, not found, or just some unexpected error. And then, so you might have a result type. User service result of A is either a failure or A. So you've got a nice, well-typed error handling. And then on top of that, you might also need to pass some context around. Like maybe you are doing some distributed tracing. You've got like a microservice architecture and you need to trace a request coming in from the front end and running through all of your services. So you might be passing trace tokens around in request headers. So maybe you have a trace token that's passed in with the request and you need to put that into all of your log messages and send it to back-end services and so on. So that means that our overall effect, our monad, ends up as a Kleisli or reader T of context to user service result of A. I mean, this is just an example. This doesn't apply to everyone's code, I'm sure, but this is a kind of pattern I tend to end up using quite a lot when I'm building kind of, web API-driven services. And then finally, you've got your actual implementation details. So how do you talk to the database to persist a user, and so on. So here, I've made the effect. I've made F concrete at this point. I've said it's persistence of type user service op. You don't necessarily need to do that. If you want to decouple at this point, you can say that F is still abstract, but it's a monad, or it's a monad error, or whatever. But just for convenience, this is one way that you can do it. So we've got one class for DB persistence, one for sending Kafka events. And then finally, just wiring it all together. So I've got just a type alias for convenience, saying my user service it's a user ops, and its F has been made concrete, so it's now a user service ops. Sorry, user service op, that's a typo. We can construct an instance of our user service, given DB persistence and Kafka events. Say we have some user details that's come in from an API request. We can construct a program to create that user by calling the createUser method on our service. But this is a Kleisli, so it won't actually do anything until we run it by giving it some context. So we construct a context with a trace token and so on, and we call program.run, and then it will actually execute. And it will do the DB persistence and send the Kafka event. Okay, so that's all I have. I talked about how we can do this abstracting over your effect, your F, in a library such as ScalaCache, how that can be quite useful for your users, give them a bit more flexibility, and then how you can do similar techniques in your own applications, even when you are the consumer of your own API. Abstract early and commit late is my mantra, I suppose. So abstract early in your design by abstracting this F. I guess until it's pointed out to you, it's not really that obvious that, say, hard coding F to be future is an implementation detail that can be abstracted over. But once you notice it, it becomes so obvious. So you can abstract over things like that. And then commit late. You want to keep everything abstract for as long as you can, and then only commit to making things concrete right at the edge of the program or the end of the world when you're wiring everything up together. As I said, this can help to kind of structure your program better, help to give you a cleaner design, and you'll just have to trust me that it also makes it more testable, because I haven't talked about that. That's all. Thank you.